right, so if y'all are ready, we'll go and get started back again. Bill wants to, he put together a special analysis working with Dieter Bullets with Agribase, agronomics, and so he's going to talk about the nearest neighbor analysis.
So field variability is something that we all know and are very familiar with. Certainly something we can't avoid. Ryan showed some great image earlier. We showed the drone reflectivity, showing you the differences in his stands that he had in that field alone. And just, we know that's just something we encounter regularly. And last year at this meeting, I was talking with Dieter Mulitz from Agribase, and I'm an Agribase user, and we were talking about this nearest neighbor analysis and ways it can help account for field variability. So I did some work this year with the nearest neighbor analysis, and basically when you open up Agribase, you can open up your experiment, and this particular case where I'll be discussing would be a location called Woodford County. But basically we ran the nearest neighbor analysis. What you have to do is you have to tell the computer how it's set up. So in this case, my plots were set up in a serpentine field. I had to list how many ranges, how many plots per range. So it basically has an idea of how your field plot is set up where you start. In Agribase, you can do the nearest neighbor analysis looking at the plots side by side, but you can also look north or south as well. And there's a feature where you can find out which one actually works best. It can run both ways and see which ways gives you your best estimate of your variability within the fields and how to account for that. So one thing I'll bring to your attention is that Agribase is changing to a new product called Genovix, and it's going to be more of, I guess, similar to like a spreadsheet type application where there's more or less windows to click instead of maybe going different ways that you've gone with Agribase in the past. So I'll bring that to your attention that Agribase will be migrating to this new system this year. So I'll talk about this nearest neighbor analysis, which is, I think, pretty valuable for crop variety trials. So this is a heat map for a variety test, and there's 100 entries, 100 wheat entries for blocks in a randomized complete blocks. And what you can see here is that we have some high yielding, 120 yield plots that are dark green, and then the ones that are white are down near 70. So a broad range in yield, which we would expect in a variety trial. And what you can see here, and this would be considered an ideal situation, is we see kind of a speckling of some high yielding ones throughout the test. We also see a speckling of some extremely low yielding genetics as well. And if this field was completely uniform, obviously our goal is to get the best estimate of genetic rank, right? That's what we're trying to evaluate is genetics, not which side of the field yielded more. And so we're going to jack up our data. So this is kind of an ideal type visual here where we have a nice distribution of genetics and no apparent trend within our field that's potentially going to alter our data and affect our interpretation of these genetics. So when selecting fields for variety trials, obviously our goal is to find an area with uniform field conditions. And some of these we can see, they're readily apparent if we have slopes or differences in contour. Obviously low-lying areas can stay wet, it can be a problem for wheat. Could be a benefit for other crops like corn and soybean. Low-lying areas potentially can be frosted. Of course, on the other side, areas with higher elevation certainly are more prone to erosion. They might have less organic matter at those locations. But some things we can see when we go to select a field, and we might not be able to avoid it, but we certainly try to avoid situations that we can see. But there's lots of things that we can't see in these fields that are less apparent, and that's what's happening underneath the soil. We can't find areas of soil compaction by just walking out into a field. We certainly can't determine the topsoil depth without taking some probing and really looking at those characteristics as well. But even if we didn't select the ideal field, there's also potential problems that can happen during the season. Management errors such as non-uniform fertilizer applications or non-uniform irrigation situations. Certainly anybody who's worked with riser irrigation knows that sometimes you'll get a clogged nozzle. A lot of times mice get shot up there and clog your nozzle. Other times you'll notice that your irrigation pipes have leaks in them. Certainly that area can saturate an area, so it can dramatically affect how the results of our tests. Pockets of disease certainly can affect a test. Animal damage, we tend to see more deer damage along woodline areas versus closer to road areas. But as we all know, that we use the coefficient of variance to give us an idea of how much variability we have within our tests. So nearest neighbor analysis is a statistical tool to help us account for field variability. What it does is it uses data from the neighboring plots on each side of each plot and compares their varietal specific data with the other reps within the test. And it kind of gets an idea, is this area higher yielding than it really should be? Or is it for some reason suppressed and the yields in that particular region are lower than they should be? Because our ultimate goal is, again, to evaluate genetic differences, not differences in soil or what have you. But the nearest neighbor analysis accounts for and adjusts for trends in field variability, thus giving us a better prediction of genetic rank. And just as technology has evolved with time, as we all know, so has statistical analysis. Analysis of variance was developed 100 years ago. That's before we had handheld calculators. So a lot has changed. We have this computing capability now that we can look at multiple different ways to run this data using advanced computation. So this is a test I had last year in 2019. It was a wheat test. Basically, it went 28 plots deep and 12 wide. And I believe the nitrogen that the farm, this was a university site, and the farm managers had some nitrogen in liquid solution, and it was the 32% nitrogen that can separate at low temperatures. And what apparently happened, I think, is that the fertilizer separated from itself, and I think they were actually pumping a lot of water over our field, and all the fertilizer was at the bottom of their tank, and all the water was at the top. Because what I had here, and I could tell just by going through the plots that it was nitrogen deficient. There was yellowing all over, but there were pockets of green. And I knew I was in trouble from a variability standpoint, just going through the field, that certain areas were green, certain areas were yellow. There was mixes of this and that. And I knew very early on that I was not going to be able to include this data in our multi-location analysis. I knew it was going to be highly variable and basically a problem. And the darker regions show the higher yielding areas, the black, and the lighter green shows the lower yielding areas. So you can see I kind of had, towards the left side of the field there, a lot of higher yielding plots and a lot of very low yellow plots kind of intermixed throughout. So my CV was about 14, which would be expected for something like that. I guess I'm surprised it was actually only 14. But so I ran the nearest neighbor analysis on this, and what it does with Agribase, it gives you an NNA weight, which 0 tells you there's no trend in the field, and a value of 1 means there's extreme trends. Basically, your data is going to be all over the place based on where it is in the field. And so a 0.55 value for me was pretty high value. I ran it on all my locations, 7 locations. I think it ran from like a 0.7 weight to the 55. I think the next lowest one was probably a 0.3 something. But this one was definitely had a high weight, suggesting that this is something we really need to look at, that there's variability in the field. And the way this nearest neighbor analysis works in Agribase is that it runs cycles. So it adjusts the data one time based on looking at how the neighboring plots did in other locations of the field. And so basically it would look at this area here and it would say, well, how did this plot do? It would look at this data here and see if these were also very high yielding here, here, and here. And if it says, no, that doesn't maybe look right, this looks like it's artificially high, it does that with every single neighbor across the whole entire test. Same likewise with the lower yielding area. It kind of detects which there's a trend for being either a high yielding or potentially low yielding based on variability within the field. So what it does is it cycles through and it does this analysis, and then it takes that data and it cycles through again, and it cycles through again, just the entire field. It works out these data. It keeps kind of massaging the data till it gets a value where the adjustment is less than 1/10,000th of the experimental mean. So once it reaches that point, it stops and says, okay, here's your values. And they give your adjusted values. They give you the unadjusted, which had I just run an ANOVA, this is what it would have been, and it lists the rank. And what I'm showing you here is after you adjust for the field variability, it does change the rank of some of your varieties. So in this case, this used to be ranked 24, 25, 36. After accounting for the field variability, they shot those way up to being the number 9, 10, and 11 highest yielding varieties within the test. And over at the end, it shows you how many places it moved up within your test, or down within your test. In this case, it added 3 to 6 bushels per acre for those particular varieties. And then at the bottom of the analysis, it shows you your CV value. Again, I was around 14, but it took the data after massaging it and accounting for a lot of this variability, it took me down to more like a 9. It increased the heritability from 0.2 to 0.4, so essentially doubling that. So after the originally data I showed you looked very similar to this, and I guess the original data set, which was just a heat map of my yields, Agribase creates a trend file, and it creates a map that looks similar to this, but you're going to see you see more of the shading just in one area, and it's kind of identifying the field and what's really going on. This is actually the trend data that it showed. So it generated this trend, and it's basically showing that you're having higher yields in this stretch here, and then lower yields these other places. So software identifies that and lets you know that's the problem. And again, there's the original data, so just showing the change between the trend and the original data from the heat map. But Agribase also gives you a printout, and it shows you, this is just the plots as you're moving from 1 to 60. So it would have been the plot starting from here, moving back and forth and back and forth. It tells you what your trend is. And when you see this type of pattern, peaks and valleys, so this is a high, potentially, there's basically your plots are saying there's a trend that this is artificially high. This is artificially low. Artificially high, artificially low. That shows us from one side of your field to the other, there's a problem. And it's a good indicator that correspond with that trend map that I just showed. So what it does, after it takes those trends, it takes all your yield data and it adjusts it to create this file. So this is now my new results yield data for each particular plot. So let me see if I have. So we went from this original data, right? Applied the trends, said, okay, we're going to factor in the trends. What do we end up with? And this is what it adjusts for. So I have some apprehension about this, just that it almost seems like magic, that it can magically account for all this, but I think there's a lot of certain methodology and computational power that can help generate these figures. But basically, it looks more like you would expect to see varietal differences within each block. You're going to see some high-yielding ones and some low-yielding ones, since these are completely randomized blocks, right? We would expect to see this type of pattern, just a speckling. So that's the primary thing I wanted to show you. In the new software that's being released, Dieter sent me some of these graphs the other day. And basically, you can also look at 3D maps. You can generate 3D maps. And this just shows the unadjusted yields where I tend to have some higher yields in that one side of the field. Shows the yield trend. Again, it's showing yellows on one side, low yielding blues on the other with a little patch in between. But ideally, if we had not had a lot of field variability, we would expect this to be more just in the green range. We wouldn't have expected to be seeing the yellows or blues or purples. Just one other side note, the new software also generates what's called a contour yield plot map, and it kind of, to me, looks like kind of the trends map in a way. It is what I first thought, but it's actually supposed to be a yield contour map. And again, it shows you that something's not uniform within your field. Basically what it's telling you is it's not more of a uniform color. This is another data set that I think the nearest neighbor weight was, I think, like a 0.37. It has some variability. My measured yield, I tended to have more green on this side and more lower yielding stuff over here. And after running it, the trend again did show that, yeah, this tended to be greener here. But the reason I'm showing this that I found was interesting is I ended up with this strip of low yielding plots here and here. And my guess is it could be like a soil compaction area due to, that's where we typically run our tram lines through with our sprayer. And I think if it butts up against the field and you run over and over and over for years and years and years, you might see something like that happen. This is some data I got from 2013, so I can't even remember what that field looked like back then, but that popped out and that stood out to me as being an interesting thing that in our measured yield, we couldn't see that at all. Basically, the computer picked up that there's something wrong here and that these are artificially low. And we need to account for those strips of low yielding potential. So again, it's the measured yield. This is how it looked like after we adjusted for the trend. So again, more what would be considered more of a random distribution of high and low yielding plots within each plot. So with that, that's the end of my presentation on nearest neighbor analysis and accounting for field variability. Any questions?
So do you need to have borders on the outside of your measured plots for this to work?
That are also measured?
Yeah.
I don't think so. I mean, the data I sent, I don't know how it handles that, but it does handle that. I know it was listed as an option within the software. I believe I saw that. Because obviously, if you start with your endpoint, there's nothing below, there's nothing on the side. I'm not sure how it accounts for that, but it does generate some number. Maybe it's a partial neighbor analysis in that situation.
So do you choose how many neighbors it's going to use in the analysis? Or
I think it only used the immediate one to the right and left, and to the north and the south. And then it takes the next plot and uses that and selects the next one. All the way down through the whole field and generates something, and it does it again and again and again until it thinks, okay, we've got this covered. So.
How does this compare to the Alpha-Lattice design? I know I've heard of both, and we've talked about this before, but Alpha-Lattice obviously got blocks within blocks, you know.
I'm not sure
Okay.
how to answer that, yeah. I would think the blocks within the blocks. You could still potentially have some variability issues, I guess. Yeah, certainly.
I've dabbled with this a little bit, and I kind of like it. It seems to bring your CVs down and smooth things out. The worse your field is, the more changes it makes.
Yes.
How do you decide whether to use this or just a standard RCB, or should you just like go with this all the time now?
Yeah, that's a great question, and that's a question that I've been asking myself, how to handle that? Do you just run it and let it work out even the small kinks in fields? Because there's always variability. I'm not sure what the best answer is, because I'm so used to just running ANOVAs that it's kind of ingrained in my system, and this is such a dramatic change, particularly in these extreme situations. It makes you think, is this really data that we need to be putting out when you have that underlying feeling that there's something wrong with it? But I think there's a case to use it all the time. If it works, if it makes a better representation of genetic rank, you should probably use it all the time. I personally haven't, but I'm just starting into this year, and inspired by a talk that Dieter gave here last year. It got me thinking, got us talking after the meeting, and that's where I'm sharing this with you. Yeah.
It's a good PhD for someone going back through all the existing data sets and running neighbor analysis on them and then comparing them with results using NO.
Yeah, I mean, you're right. I mean, there's so much power in these models, these algorithms, that you can, you could do a PhD on it, I'm sure. Trey, do you have a question?
Yeah. People who have studied the different analyses have some real serious problems with nearest neighbor. And I can't remember what they are, but I think just sitting here thinking about it, it seems to me like there's a possibility of adjusting for areas that you really want to be sampling, that the trial was designed to sample.
Yeah.
So that there could be a confusion between, or a confounding effect of the genotype that you're actually trying to test and a color that might be showing up in part of a field. So that's one way of thinking about it. And the other way of thinking about it is that we rarely make decisions based upon a single trial, right? So we're going to be putting combinations of trials together, and I'm not sure how this would work for that when you're trying to put those data sets together, that you may actually, even though you're showing some heterogeneity in the field or a trend in the field, it may be something that you want to be sampling. It may be creating another environment that's going to go into that mean and make that mean more robust because you have sampled it.
That's right, because all our environments are different environments anyways, and
so it's kind of like
combined over locations and years.
When we're doing something different from our ANOVA that we have accustomed to do it, and I do spatial analysis. Other people do different kinds of spatial analysis than nearest neighbor. That we have to ask ourselves, why has ANOVA worked so well for us over time? Right?
Yeah.
So the means that we get out of ANOVA, just generally taking our means, over time have worked pretty well, especially when you get a lot of numbers that are going into those means. So, I'm just...
Yeah, I think, it almost sounds too good to be true. Yeah. And I think what I want to start doing is, in all our variety tests, we have some varieties that are branded. And most of the time we don't know what those are, but sometimes we do know. And I think what we need to do maybe is take certain varieties and see if we know you have the same variety in your field 3 or 5 times, say, in your test. Look at it, run the nearest neighbor analysis, and see if it pulled them closer together or pull them apart. Or maybe we need to have more checks in our field to help us figure out, is this really a practical, useful tool? Because if it's pulling them all together, then that's going to tell you that this is a good thing. If it's starting to pull it apart or not giving you what you want, aside from the value that you mentioned, just in having data for what it is,
Your model R squared kind of tells you a lot about how well your ANOVA model is fitting, right? So if you got a model R square of 0.9, then I wouldn't be running any nearest neighbor analysis on it at all. My model is doing really well. If you have a R square of 0.2, then your trial is probably pretty messed up and you should not
Yeah.
use that data.
And that's a great point. Maybe like we need to define and think about this in the future, like certain parameters where we might apply this and where we might say, no, we don't want to mess with it. Anyhow, thank you.